Hello everyone, my name is Max Scherer and I will present our paper Reliability Prediction of Self-Adaptive Systems Managing Uncertain AI Black Box Components. The second author who contributed to the paper is Ralf Reusner from the Karlsruhe Institute of Technology. In the last decades, the field of artificial intelligence, or AI, made some remarkable progress. Especially deep learning, a subfield of AI, is used in many use cases such as autonomous driving or human-robot interaction. However, deep learning networks implement very complex model structures so that predictions made by the network are neither transparent nor comprehensible. The lack of comprehensibility and the inherent data dependency might result in incorrect predictions that are especially concerning in safety-critical domains such as autonomous driving. This problem is not new in AI research. There are several approaches that attempt to make AI models more robust. However, they also cannot guarantee the correctness of predictions. Other approaches allow the detection of malicious input data that can potentially lead to incorrect predictions. Such techniques, however, answer the question of how to possibly detect such inputs, but do not elaborate on the question of how to react. Therefore, we advocate the use of MAPK-based self-adaptive systems that provide a holistic framework where approaches for detecting incorrect predictions can be embedded and that also defines concepts for planning and executing countermeasures such as the transitioning of the system to a fail-safe state or switching component implementations. Secondly, when using self-adaptive system to maintain reliability attributes, a couple of design decisions must be taken into account. For instance, which input data checking algorithm should be considered in the monitor phase, or which reconfigurations are supposed to be used in general. Each decision has a different impact on the reliability of the system and is preferably evaluated before the system is implemented. Therefore, we present a model-based approach that enables reliability prediction of self-adaptive system managing uncertain AI black box components at design time. The approach draws on ideas and concepts from the field of model-based quality analysis that have proven successful in predicting quality attributes of software architectures represented by models. In summary, this talk addresses the following research questions. RQ1, how to design MAPK-based self-adaptive systems managing AI black box components with uncertain outcomes. And RQ2, is it possible to predict reliability properties of systems with uncertain AI black box components at design time? The contributions are initial ideas and concepts on how to use self-adaptive systems in this context as a holistic framework, and a novel approach to predict and evaluate how they meet reliability objectives at design time. The most challenging task of a self-adaptive system is to reason about the state of the AI black box component in order to take action in situations where incorrect predictions may occur. One way to do this is to observe and identify malicious input data that is passed to the black box. Based on the monitored input data, the self-adaptive system decides in the analyze phase whether adaptation is required. More formally, let an AI black box component be a function denoted as B that maps an input data from an input space to elements of the n-dimensional output space. The state of the black box B is hidden due to the lacking transparency and comprehensibility. However, it is possible to draw conclusions about the true state, for example by estimating the conditional probability distribution of observing an incorrect prediction given an input data X. The distribution can be queried in the analyze phase in order to determine whether a reconfiguration should be triggered. However, estimating the distribution with respect to the input space is actually impractical. For instance, consider the image, or rather the pixel space in perception learning tasks, which is extremely large. Therefore, we need to condition the distribution on other properties that are more manageable. Instead of drawing conclusions about the hidden state of B based on the input data, we can augment the monitor phase by a set of observable properties. In addition, we make an assumption that is called missing at random. Generally, the missing at random assumption requires conditional independence between the random variables of the hidden state and their observations, given a set of observable variables. So, roughly speaking, this means that the probability of observing a correct or incorrect prediction and a certain input data is independent given the set of observable properties that augment the monitor phase. The assumption implies that we can decouple the observations and only need to focus on the monitored properties. More specifically, in the analyze phase, only the monitored values of the properties are relevant to reason about the true state of the AI component and to determine whether adaptation is required. As an example, consider a non-mobile robotic system consisting of a single arm equipped with a camera to assist in a human-robot interaction use case. The safety of a human worker depends on the accuracy of the AI detection component because undetected body parts are not considered in the trajectory planning. As a result of a domain analysis, or maybe by consulting a domain expert, brightness variations or sensor noise are identified as the two main factors or uncertainties responsible for producing incorrect predictions. In this case, additional monitors augment the monitor phase to specifically observe the brightness and sensor noise levels. Finally, in the analyze phase, the probability of a false prediction is determined by the monitored brightness and sensor noise levels. The second part of this talk is about reliability prediction of self-adaptive systems managing uncertain AI components. We extend an existing reliability prediction approach for static software systems. The approach is based on an architectural description language for modeling software architectures, called the Palladio Component Model, or PCM. In a nutshell, the approach extends PCM by additional hardware, network, and software failure annotations, which specify the probability of failure. Based on the annotations, the PCM model is transformed to a Markov chain for predicting the probability of success or failure of the overall system. We extend the reliability approach by considering an incorrect prediction of an AI model as a special kind of software failure. Additionally, we apply a sensitivity analysis to the trained AI model with respect to the monitorable properties. The result of the sensitivity analysis is a probability distribution determining the probability of observing false predictions for different property values. The sensitivity distribution is queried to determine the probability of an incorrect prediction for a specific property value. The failure probability of the AI model is adjusted in the PCM model, and the success probability is determined by applying the conventional reliability prediction approach again. We integrated the approach in our model-based framework from previous work for validating self-adaptive systems at design time. The framework provides a probabilistic environment model to capture and sample different property values. The framework is complemented by a prototypically implemented reconfiguration strategy and evaluates the decisions made by the strategy based on the reliability prediction by our approach. We evaluated the applicability of our approach by a proof of concept. Due to limited time, we can't go into detail here, but we encourage anyone interested to take a look at the paper. Roughly summarized, we applied our approach in a human-robot interaction scenario. Here, a self-adaptive system has to maintain two quality objectives. First, reliability by preventing possible incorrect predictions of the AI perception component, and second, the overall performance of the system. The results of the proof of concept have shown that our approach allows software engineers to compare different strategies in terms of their effectiveness with respect to quality objectives and are in line with our expectations. In summary, we addressed the first research question by decoupling the observation process, an example by augmenting the monitor phase with additional observable properties, which enable reasoning about the true state of an AI component. For the second research question, we extended an existing model-based approach for reliability prediction and integrated it with our model-based framework from previous work for validating reconfiguration strategies. We demonstrated the applicability of our approach by a proof of concept. However, the proof of concept does not validate the accuracy of our approach. Therefore, in future work, we plan to investigate the research questions more intensively by comparing our prediction results against the baseline. Okay, then thank you very much for listening to our talk, and I'm looking forward to the conference.